All right, Chapter 6, Section 4, Matrix Operations and Solving Linear Systems Using an Inverse Matrix. We have a few objectives in this section. First, the order of a matrix, and also how to tell whether two matrices are equal. And then adding and subtracting matrices, multiplying matrices, writing a linear system as a matrix equation, and then solving linear systems using an inverse matrix. All right, so let's get into it. Okay, example number 1, determine the order of the following matrices. Let's look at the very first matrix. All right, here is the very first matrix they want us to consider. And finding the order of a matrix is really straightforward here, folks. All you have to do is count how many rows by how many columns. So the rows run horizontally, so you have 2 rows, and the columns run vertically. So you have 1, 2, 3 columns. 2 rows by 3 columns, so therefore we would say the order of this matrix is 2 by 3. 2 by 3. This is a 2 by 3 matrix. Now it's important that you understand that the number 2 right here represents the number of rows, and the second number 3 represents the number of columns. Also, of course, don't think this is 2 times 3. This just is our way of saying 2 by 3. This is a 2 by 3 matrix. Okay? That's it, guys. Let's look at a couple more matrices and find their order. All right, here's our brand new matrix. To determine the order of this matrix, all you have to do is count how many rows. 1, 2, 3 rows, and 1, 2, 3 columns. So this matrix is a 3 by 3 matrix. Now, notice that the number of rows is exactly equal to the number of columns. Oops, sorry. All right, let me get that back on the board for you. It's a 3 by 3 matrix. Now look at this. The number of rows is equal to the number of columns. Whenever you have the same number of rows as columns, you call this a square matrix. All right, so this is a square matrix because the number of columns is equivalent or the same as the number of rows. All right, cool. Let's look at another matrix and determine its order. Okay, guys, here's our brand new matrix they want us to consider. Now let's count the number of rows and count the number of columns. Now I invite you to pause this video and determine the order. Write it down in your notes, and let's see if you and I agree. All right, so I count 2. I hope you actually did that. I count 2 rows, and I count 1, 2, 3, 4, 5 columns. So this is a 2 by 5 matrix. It's not a square matrix because the number of rows is different than the number of columns. Okay, cool. We know how to find the order of a matrix. Now let's talk about equality of matrices. 2 matrices are equal if they have the same order. Number 1, they have to have the same order. But not only that, they have every entry in the same position in both matrices are equal. So you have to have the same order and every single entry in the same position must be the same. Let's look at some examples. Okay, let's look at this second example. Answer the following questions regarding 2 equal matrices. All right. So this matrix, which is 2 by 1, right? 2 rows by 1 column, is equal to another 2 by 1 matrix. And the question is, what is the ordered pair x comma y? So basically, what is x equal to and what is y equal to? Now, to answer this question, we have to remember that 2 matrices are equal if they have the same order. So we have 2 by 1. This is also 2 by 1. That's good. But every single entry in the same position in both of these matrices have to be equal. So in this first row, first column entry has to be the same as this first row, first column entry. So in other words, x is going to have to be equal to 3. this second row first column entry must be the same as the second row first column entry of the other matrix, so y has to be 8. So x has to be 3, y has to be 8. So here's our answer. The ordered pair x comma y is 3 comma 8. That's what x and y would have to be in order for these two matrices to be equal. I hope that was straightforward for you. Let's look at another. So now they've given us two matrices, and they're telling us that these two matrices are equal. Look at the order. This is a 3 rows by 1 column matrix. In other words, 3 by 1. This is also a 3 by 1 matrix. And they are only equal if they have the same order and every entry in the same position in both matrices are also equal. Here comes the question. What is the ordered triple x comma y comma z? In other words, what's x, what's y, and what is z? Well, in order for these two matrices to be equal, this x value, which is in the first row, first column entry, must be equal to the first row, first column entry over here. So x has to be -2, y would have to be 4, and z would have to be 9. So that's my ordered triple. -2, 4, and 9. That's the only way these two matrices will be equal. All right, what system of equations does this equality represent? All right, so what they want us to do is rewrite this equality but use a system of equations instead. So a system, we always use a brace like this, right? And the first equation within the system will correspond to this entire first row. So you'll have x minus 2y must be equal to 5. Now you know that has to be true because these two matrices are equal. And what do you have here? Over here you have x minus 2y, and over here you have 5. So these entries must be the same. So then you're going to have x minus 2y is equal to 5 is the first equation, and then 3x plus 5y has to be the second. That's the only way that these two matrices will be equal. Pretty straightforward, I hope, so far. Let's continue. All right, guys, we're moving on to addition and subtraction of matrices. All right, the next objective. So what we have here, you are given two matrices. Matrix A is 2, 1, -3, 6, 7, 8. And then matrix B is -3, 4, 0. And then the second row is 6, -2, 9. Notice that both of these have the same order, don't they? You have a 2 by 3 and another 2 by 3. What they're going to ask you to do is to operate on these two matrices. So let's look at the first set of instructions here. The first thing they want us to do is to find the sum A plus B. In other words, they want us to add our two matrices together. All right, so I hope you find this to be really straightforward. What I'm going to do is I'm going to write down matrix A, which is 2, 1, -3, 6, 7, 8, and also B, and we are adding them together. Now, the first thing I want to tell you, and this is really important, worth writing down, the only way you can add or subtract matrices is if they have the same order. The order must be the same. Okay, I squeezed it in right there for you, but you might want to write this down for your notes. Now, because we already identified that the orders are the same, we can go ahead and add these two matrices together. Now, adding a matrix to another is really straightforward. All you have to do is take every entry in matrix A and add it to its corresponding entry in matrix B. In other words, 2 must be added to -3. 1 must be added to 4. -3 must be added to 0, and so forth. In other words, you take the first row, first column entry and add it to this first row, first column entry. Let's see. You would take this second row, first column entry and add it to this guy's second row, first column entry, and so forth. Every entry must be added to its corresponding entry. All right, so here is the sum right here. Okay, we are going to have 2 plus -3. What does that give us? -1. And then we'll have 1 plus 4. What does that give us? 5. I hope you find this really straightforward. -3 plus 0. That's right, -3. 6 plus 6, 12. 7 plus -2, 5. And finally, 8 plus 9, 17. So that's how it works, folks. This is the sum A plus B. This is the matrix A plus B. Notice that the order of A plus B is the same as the order of A and the order of B. All right? So this is our final answer. Pretty cool. The next thing they want you to find with the same two given matrices is A minus B. A minus B. Now, the only way we can evaluate or find this difference is if the order of the two matrices are the same, which they are. They're both 2 by 3 matrices. We said that earlier. So we're able to actually subtract. Now, be careful. Subtraction, you have to make sure you write this in the right order. So we have matrix A first, and then minus matrix B. Okay? Okay, guys, and the way we're going to do this is exactly the same way we found the sum. That is to say, we're going to take every entry in matrix A and subtract it to every corresponding entry in matrix B. I stuttered there because I should actually rephrase that a little bit better. When you're doing subtraction, performing subtraction, it's really taking every entry in matrix B and subtracting it from every corresponding entry in matrix A. In other words, it'll be 2 minus -3. It'll be 1 minus 4. It'll be -3 minus 0, and so forth. All right, let's do it. I suggest you pause this video and try this on your own. I think you can definitely get this difference. So I'll give you some time to do that. All right, good job. I hope this is the difference that you found. Notice that A minus B is a 2 by 3 matrix, just like matrix A, just like matrix B. The last thing they want you to find is B minus A. It's almost very similar to what we've already done. Actually, we did A minus B, right? This is B minus A. So let's make sure we get the order correct here. So it's B first. So then it's going to be -3, 4, 0, 6, -2, 9. That's the first matrix we're starting with, right? This is matrix B. And then we're going to subtract matrix A. All right, cool. So we have matrix B minus matrix A. And it's done the same way, corresponding entries. So first you're going to have -3 minus 2, which is -5. And do this for every entry, all right? I'll do one more. 4 minus 1, so that's going to be 3. Can you pause the video and finish this? All right, I hope you and I agree on our difference, B minus A. So good job, you guys. We know how to add and subtract matrices. Pretty straightforward, isn't it? Let's move on. Okay, you guys, we covered objective 1, which is the order of a matrix and equality of matrices. We've covered objective 2, which is the addition and subtraction of matrices. Now we're going to objective number 3, which is matrix multiplication. All right, to get us started in example 4, we have the same two matrices here, and we're gonna multiply. We're gonna operate. The first type of multiplication is called scalar multiplication, and that is when you multiply a matrix by a real number value. For example, look at this. Find 3A. 3A means you want to take matrix A and multiply it by 3. This is a type of scalar multiplication. So in other words, you're going to take the number 3 and you're going to multiply matrix A by 3. All right? In other words, you're going to triple it. Now, the way this works, and you can probably guess how this is going to work, right? What would be your guess on how to perform this scalar multiplication? If you're thinking that we need to distribute the 3 to every single entry, you are absolutely correct. To multiply matrix A by the scalar 3, all that means is you take every single entry in matrix A and you multiply it by 3. So it goes to everybody, if you will. All right? So our entries for our product here will be 3 times 2, which is 6, 3 times 1, which is 3, 3 times negative 3, which is negative 9. Now I'm in the second row. 3 times 6 is 18, 3 times 7 is 21, 3 times 8 is 24. And that's it. This is 3 times A. Isn't that pretty cool? This is scalar multiplication, the first kind of multiplication that we're looking at. The next part says find negative 2 times B. This is still scalar multiplication. Now we're going to take matrix B and multiply it by negative 2. Okay, negative 2 is called our scalar. It's a real number. And we're basically going to distribute negative 2 to every single entry in this matrix. So our final answer, actually, can you do me a favor and can you pause the video and find what negative 2b is? Just multiply every single entry by negative 2 and that'll be your answer. Go ahead. All right, I hope this is the answer that you got after multiplying every single entry by negative 2. All right, everybody, you know how to multiply a matrix by a scalar. Now let's look at another kind of matrix multiplication where we multiply a matrix by another matrix. All right, you guys, example 5, consider the following matrices. You got matrix A here, you got matrix B, C, D, and E. Notice the order of each of these matrices. Matrix A is a 2 by 3. Matrix B is a 2 by 3 as well. Matrix C is a 2 by 2. Matrix D is a 3 by 3. And matrix E is a 3 by 2. Out of these 5 matrices, which one or which ones can be called a square matrix? That's right. Matrix C and matrix D can be considered square matrices because the number of rows is equal to the number of columns. See? 2 rows, 2 columns. So it's a square matrix. This is also a square matrix because you got 3 rows, 3 columns. All right? All right, this example is going to focus on multiplying a matrix by another matrix. Now, when you added and subtracted matrices, all you needed was for the 2 matrices to have the same order. I'll say that again. When you added and subtracted matrices, all you needed was for the 2 matrices to have the same order. However, when it comes to multiplying matrices, which is what we're about to do next, you need the 2 matrices to have something in common, and that is the first matrix. The number of columns in the first matrix must be equal to the number of rows in the second matrix in order for you to multiply. Okay, go ahead and add this to your notes here. Multiplication of 2 matrices requires that the number of columns in the first matrix equals the number of rows in the second. Number of columns has to be the same as the number of rows. Columns to rows. Columns of the first matrix must be equal to the number of rows of the second matrix. Okay? If that's true, then you can multiply. If that's not true, then you cannot multiply. The multiplication is not defined. Now, the product of 2 matrices will have the same number of rows as the first matrix and the same number of columns as the second matrix. All right? I'll give you an example before we actually look at multiplying some of these matrices that were given in this problem. Now, watch this. Let's say you have matrix, let me not use any of the letters that were chosen above. How about matrix H and matrix M, okay? And let's say matrix H has order 2 by 3. Let's say matrix M has order 3 by 2. Am I able to multiply these two matrices? The answer is yes, because the number of columns of the first matrix equals the number of rows of the second matrix. Because those two numbers are the same, you're able to multiply. Now, the second thing is the product of the two matrices will have the same number of rows as the first matrix and the same number of columns as the second matrix. In other words, when I multiply H and M together, right? Matrix H times M. Here, let me actually do it like this. Matrix H times M, like that. What will be the order of matrix H times M? Well, it'll be the same number of rows in the first matrix by the same number of columns in the second matrix. So for this example that I'm making up right now, the order of the product will be a 2 by 2. That many number of rows by that many number of columns. Okay? I'll reiterate that each time we do a problem for this example. All right, let's go. Let's look at an example now. So this is example 5. They've given us 5 different matrices. Now they're going to start asking us to operate on these matrices. Start multiplying one by another. All right, so let's go for it. All right, the first product they're asking us to find is A times B. Take matrix A and multiply it by matrix B. All right, guys, let's see if we can even do this. Matrix A has order 2 by 3. Matrix B has order 2 by 3 as well. In order for me to multiply, in order for the multiplication to even be defined, the number of columns of the first matrix must be the same as the number of rows of the second matrix. And that's not true here. The number of columns is not equal to the number of rows. So the multiplication is not defined. I cannot find the product A times B, undefined. Okay, I put this product as undefined, so I can go to the next. A times C is what they're asking you. A times C. All right, let's see if we can do it. Matrix A has order 2 by 3. We already said that. Matrix C has order 2 by 2. All right, can we multiply? Well, matrix A has 3 columns. Matrix C has 2 rows. Those two numbers are not the same. So once again, this product is also undefined. All right, so let's move on to the next question then. Okay, the third question, find this product C times A. All right, let's see if we can do this product. Okay, matrix C is a 2 by 2 square matrix. Matrix A is a 2 by 3. Can we find the product? Well, since the number of columns of C is equal to the number of rows in A, this product is defined. So now we can go find it. But before we find it, can we determine the order of the product? Now remember, the order of a product will be equal to the number of rows of the first matrix by the number of columns of the second matrix. So in other words, my product will have order 2 by 3. 2 by 3. In other words, when I'm done, I should have a matrix that has 2 rows and 3 columns. All right. One more thing, guys. Notice that the product CA is defined, but yet the product A times C was undefined. So this is what I wanted you to add to your notes. In the previous example, we were asked to find the product A times C, and we couldn't. It was undefined. But then when you turn the multiplication around, C times A, that is defined. That shows you that matrix multiplication is not commutative. In other words, A times C is not the same thing as C times A. When you multiply, multiplication of real numbers is commutative. In other words, 3 times 5 is the same thing as 5 times 3. 2 times 7 is the same thing as 7 times 2, right? Multiplication is commutative. But when it comes to matrices, matrix multiplication is not commutative. The order in which you multiply matters. Okay, we're ready to find the product C times A. Let's do this. All right, I have matrix C here and matrix A here. So this is going to be C times A. Now, pay attention very closely, please. The way I'm going to multiply these two matrices is, first I'd like to get what my answer is going to look like. We do already know that the product will have order 2 by 3. So this is an example or a template, if you will, for my answer, 2 rows by 3 columns. Now watch this, and this is very important. The way I'm going to get this entry in the first row, first column entry, now listen to my vocabulary, the first row, first column entry will be found by multiplying the first row by the first column. This first row by this first column. So you can see I'm going to do 9 times 2, right? This is the first row by the first column. Here, this is what I can do for you. I think this will be really good. Is if I highlight this first row so you can kind of visually block that out. That's what we're multiplying, okay? So we're going to do 9 times 2. Watch this. Follow me now. 9 times 2. Now watch this. Plus 5 times 6. Okay, did you get that? 9 times 2 and then plus 5 times 6. All of that will give me this first entry, which is the first row, first column entry. Okay, so let's figure out what that is. Okay, so we know 9 times 2 is 18, and then 5 times 6 is 30. So let me erase this real quick. So we know 18 plus 30 is 48. So 48 is this entry in my product, in my answer, the first row, first column. Okay, entry. All right, let's see if we can do this again for the first row, second column entry. First row, second column. That means I'm going to multiply my first row by the second column. Okay, so what I'm going to do first is 9 times 1 and then plus 5 times 7. All right, so 9 times 1 plus 5 times 7. We know that gives us 9 plus 35. All right, so 9 plus 35 is 44. So you're going to see me fill that in my answer, 44. Okay, so that's what we're doing to get our product. All right, let's go for the next. What are we after now? This entry, what is this? The first row, third column. First row, third column. First row, third column. Okay, that means I'm going to take this first row and multiply it by the third column. Okay, that means I'm going to do 9 times negative 3 plus 5 times 8. Okay, 9 times negative 3 is negative 20. I'm going too fast there. 9 times negative 3, let me use parentheses there, plus 5 times 8. 9 times negative 3 is negative 27, and 5 times 8 is 40. Let me close that bracket there for us. That and like that. And negative 27 plus 40 is 13. So that's what this number is going to be right there. Cool? I'm hoping that you're getting how this process works, okay? So we got the first row of our product to be 48, 44, and 13. Okay, guys, let's go for the second row. Let's go for the second row in my product. Okay, guys, in order to get the second row in my answer in the product, this entry right here that I'm pointing at would be the second row, first column. Second row, first column. So let's go to the second row and first column of my factors, of my matrices. So this is where I want you to focus on. These are the entries we're using. Second row, first column, so that we can get the second row, first column entry of my answer. All right, here we go. Are you ready? So we're going to do 3 times 2 plus 2 times 6. I'll say that again as I write it. 3 times 2 plus 2 times 6. Okay? That would give us 6 plus 12 for this entry, which is 18. So there's that entry. Cool? All right, let's go for this one now. What is this? Second row, second column. Second row, second column. Second row, second column. All right, I've highlighted what we're focusing on here. So we're going to go 3 times 1 plus 2 times 7, which is 3 plus 14, which is 17. Cool? All right, last one. We want second row, third column. Second row, third column. Second row, third column. So I am now going to circle that third column there for us. -3 and 8. Leave that minus sign. All right, cool. So let's do it. So I am going to be multiplying 3 times -3, 2 times 8. So 3 times -3 plus 2 times 8. This gives us -9 plus 16, and that sum there is 7. So there's my product. I knew that was a process. I knew that was going to be a process for us, so I wanted to make sure I laid it out as slow as I can, as thoroughly as I can, all right? So this is our product, and notice that the order is exactly the order that you and I thought it would be in the very beginning of the process. 2 rows by 3 columns, so it's a 2 by 3, like we expected. Okay, guys, we're still in that same example. Now they want us to find the product DE. All right, so let's see if you and I can even find this product. If you need to scroll back a little bit, you can, in order to see what matrix D is and what matrix E is. All right, so matrix D, if you scroll back, you can pause the video if you like. Matrix D, make that look like a D, is a square matrix. It's actually 3 by 3. All right, now matrix E is a 3 by 2. All right, so are we able to find this product? Yes, because the number of columns in D is equal to the number of rows in E. Very good. So this product is defined. So we know this product is defined. We're able to find it, and the order of the product will be 3 by 2. 3 by 2. That means when we're done, we expect to have a matrix that has 3 rows and 2 columns. All right, let's go find this product. Woo, I'm excited. Aren't you excited? Let's do it. All right, guys, let me fill in for us these matrices, D and E. All right, there's matrix D, there's matrix E. This is matrix D here, and matrix E. Okay, guys, here we go. In order to get, remember this is going to be a 3 row by 2 columns, okay? In order to get the first row, first column entry, I'm going to look at the first row and my first column. First row by first column will give me this first row, first column entry. All right, so let's do it. So we're going to do 7 times 4 plus 6 times 5 plus 1 times 1. All right, let's see if you can figure out what all of that is. 7 times 4 is 28. 6 times 5 is 30. 1 times 1 is 1. So it's 28 plus 30, which is 58, plus 1. So 28 plus 30, 58 plus 1, 59. All right, so 59 is going to be that entry there. Okay? All right, let's go for the next one. And I might have to write a little smaller here. We're going to go now for the second row, or actually let's stick with the first row, shall we? So first row, second column. First row, second column. First row, now second column. All right, here we go. 7, 6, and 1, right? That's first row, and negative 3, 2, 7 is second column. All right, that's going to give us this entry. First row, second column. All right, let's go for it. And I might have to write a little smaller here. So it'll be 7 times negative 3. Okay, I'm going to see if I use parentheses, if that helps me a little bit. Plus 6 times 2. I think I'm going to run out of space here. Plus 1 times 7. All right, so I'm sorry that I went off a little bit. I just need a little bit more space there. You know what? Let me go back. That's bothering me. Let me go back and make a little more space for us. Okay, guys, I moved everything over just a little bit. So please allow me to do that one more time. So the first row and the second column will end up being 7 times negative 3. And then it'll be plus 6 times 2 plus 1 times 7. Okay, so let's see if we can do this arithmetic here. This is, I'm going to do the positive ones first, okay? So we got 6 times 2, which is 12, plus 1 times 7, which is 7. 12 plus 7 is 19. 19 minus 21, negative 2. All right, so I got negative 2 for this entry. Cool? Okay, guys, let's go for the second row, first column. Second row, first column entry. Second row, first column entry. I'm going to highlight that for you. I hope that's helping. Second row, first column entry. All right, let's go for the product. Here we go. So here we go. Negative 1 times 4. I'm going to start using parentheses here. Plus 5 times 5. Plus 4 times 1. Okay, let's figure out what that is. I like to do the positive sums first. So the positive products, really. 5 times 5 is 25. 4 times 1 is 4. So it's 25 plus 4, 29. 29 minus 4 is 25. So then this entry here is 25. Cool deal. All right, let's go for this next. Second row, second column. Second row, second column. All right, let's go for it. Second row, second column will be negative 1 times negative 3. Okay. Plus, let's see, plus 5 times 2. Plus 4 times 7. Now, I can't see you, but I wish we were doing this face-to-face so that I can see your work to see if you're actually getting this, if you're following. Because this is pretty exciting for you to master matrix multiplication. All right, cool. So what is this? Let's get all of our positive products. Actually, they're all positive. It's 3, positive 3, positive 10, positive 28. 28, I always leave 10 for the end. So 28 plus 3 is 31, plus 10 is 41. So that's this number here. Cool, we're almost done. Let's go for third row, first column. Third row, first column. Okay, guys, we're after the third row, first column entry. Third row, first column entry. I've highlighted those rows for us. Here we go. 3 times 4 plus 2 times 5 plus 8 times 1. What is all of that? 12 plus 8 is 20 plus 10 is 30. Alrighty, just got one more entry to go. What is that entry? It's the third row, second column entry. Third row, second column. All right, here we go. Third row, second column for the win. All right, here we go. We're going to start this off with 3 times negative 3 plus 2 times 2 plus 8 times 7. All right. Let me make sure you can read this number here. Make that look like a 2. That's what it is. All right, cool. So what is all of this? This is 2 times 2, which is 4. 8 times 7 is 56. 56 and 4 make 60. 60 minus 9, 51. So that's the number here. All right, guys, this is my product. This is my final answer. This is D times E, and it is 3 by 2, like we had said it was going to be in the very beginning. 3 rows by 2 columns, 3 by 2. All right, that's matrix multiplication. Cool deal. We're off to our very last objective, which is solving matrix equations, or solving systems of equations using a matrix equation. All right, you guys. Example 8 says, what system of equations does the matrix equation represent? All right, so let's think about this. You have a product of matrices here, right? Is this multiplication defined? Like, can you find it? Well, let's think. This first matrix has order 2 by 2, and the second matrix has order 2 by 1. So yes, this multiplication on the left-hand side is defined because the number of columns is equal to the number of rows, okay? You know what might be confusing is I'm using x's here and I'm using x's here. All right, these x's here just mean 2 by 1 for order. That x is a variable. You know what might make it a little more clear is, what if I made these right here a little bigger than normal, you know? So like 2 by 1, 2 by 2, all right? I think that's better. So the multiplication on the left-hand side is defined, and we know that the product will be a 2 by 1 matrix, okay? If you multiply these two out, notice what you get on the left-hand side. When you multiply, okay, you're going to get, let me see if I can highlight it for you. You would take the first row and multiply it by the first column. So first row, first column, 3 times x plus 4 times y. 3 times x plus 4 times y. There's your first row, first column entry. Okay? The next one will be the second row multiplied to the first column. So 2 times x plus 5 times y. This is matrix multiplication exactly the way you and I were doing it just a minute ago in the previous example. Okay? This is 5, 8. All right. So this is what we have. If you multiply these two matrices together using the algorithm or the process that I showed you in the previous example, you get 3x plus 4y and 2x plus 5y. All right? So what we can do is we can equate this to the system of equations, and this is what they're asking us to do. The only way that these two matrices are equal is if they have the same order, which they do. It's 2 rows by 1 column. This whole expression is together, so it's all 1 column. And the only way this matrix is equal to this one is if every entry in this matrix is equal to every entry in this matrix, right? Its corresponding entry. In other words, 3x plus 4y must be equal to 5, and 2x plus 5y must be equal to 8. This is the system of equations that is being represented by this matrix equation. I want you to notice something here. I'm going to create some space here. I'm going to erase some things that I wrote. I want you to notice something. Look at this system. What are these numbers? 3, 4, 2, and 5. 3, 4, 2, and 5. Aren't those your variable coefficients? 3, 4, 2, 5. All of these are your variable coefficients. Because of that, this matrix is called your coefficient matrix. And then when you look at the system, it should be obvious that our variables are x and y. So then this matrix here is called your variable matrix. And finally, so this is your variable matrix. Finally, you have 5 and 8. What are these? These are your constants. So then this can be considered your constant matrix. My point is that when you have a matrix equation, this is a matrix equation because it's an equation filled with a bunch of matrices. In a matrix equation, you have 3 pieces. You have your coefficient matrix. These are all your variable coefficients. You have your variable matrix, and you have your constant matrix, all right? And you can see how it relates to your system. Okay, you got your coefficients, 3, 4, 2, and 5. You got your variables, x and y, and you got your constants, 5 and 8. All right, example 9. This one's going to be short. Write the system as an equation involving matrices. All right, so here we go. So if you remember from what we just said, you have your coefficient matrix, then you have your variable matrix, and this is all equal to your constant matrix. Okay. All right, so all we have to do is fill it in. What are your coefficients in the first row? Your variable coefficients in the first row. 1, -3. That's right. 1 and -3. What are your coefficients, variable coefficients in the second row? 4 and 7. Your variables are x and y, and your constants are 11 and 6. There it is. This matrix equation represents the system. Very good. Look at this system. Write this system as an equation involving matrices. All right, cool. So let's do it. So you're going to have your variable coefficient matrix. So coefficient matrix here. You're going to have your variable matrix. There's 3 variables. And this will all be equal to your constants. And you got 3 constants. All right. All right, cool. What are your variable coefficients in the first row? 2, -4, 1. And then you got 1, -3, 1, 1, 2, 1. What I just listed there are all of your variable coefficients. Now, what variables do you have? X, y, and z. What are your constants? -3, -4, and 1. That's it. That's all they wanted us to do. All right, so you got your coefficient, variable, and constant matrices. All right, everybody, this is the last objective for this section. We're going to be using something called the inverse matrix to solve this system, okay? So let me walk you through this example, and we're going to solve this system. We've solved systems like this using substitution method, the elimination method. You can even graph to solve this system. We know how to solve this system using matrices, and now we're going to solve it using an inverse matrix. Like so. Now, you and I know that whenever we're looking for a variable or for an unknown, let's say an unknown rather, when we're looking for an unknown, in algebra, we isolate the unknown. That is, we get it by itself on one side of the equation. Well, in this case, we're looking for x comma y, the point at which these 2 lines intersect. These are in linear equations in 2 variables. So graphically speaking, we're speaking of 2 lines, and we want to find the point of intersection, if it exists. So you and I are looking for the coordinates x comma y, an ordered pair. So we want to isolate the variable matrix. So this is the idea, guys. In order to isolate the variable matrix, what we're going to do is multiply both sides of this equation so that this variable matrix is isolated, so that it's all by itself. And what will do that for us is if we multiply on the left-hand side right here, both sides on the left-hand side, by the inverse of this 2 by 2 matrix. I'll say that again. If we multiply right here on the left by the inverse of this 2 by 2 matrix, then this variable matrix will be isolated. Now, let me show you an easy way to get the inverse of a 2 by 2 matrix. Okay, this is a quick way to find the inverse of a 2 by 2 matrix, which is what you and I need for that problem we're working on. If matrix A is equal to this 2 by 2 matrix, which is A, B, and C, D, then A inverse, okay, will be equal to 1 over A times B minus B times C times the matrix, the 2 by 2 matrix with these entries. So let me show you what happened here. A and D swap places. Okay? And then B and C, they didn't swap places, but they just became negated. Okay, the opposite of those entries. So when you have a 2 by 2 matrix, the inverse will just be swap these two coordinates right here, A and D, and for B and C, just take the opposite of what you see. Don't forget about this fraction out front though, 1 over AD minus BC. This right here, AD minus BC, actually has a special name called determinant. Just the denominator itself. So AD minus BC, that expression down there is called the determinant. You'll hear more about that in another section. All right, so this is what we need to do, guys, in our problem. We need to find the inverse of our 2 by 2 matrix, and this is how we find it. All right, so let's go back to our problem now and find that inverse matrix. So this is where we left off. And what we need to do is multiply on the left-hand side here by the inverse of this matrix. So let's do it now. Tell you what, let's find the inverse matrix first before we actually start multiplying. So here it is, 1 over AD minus BC. So it'll be 1 over, okay, AD minus BC. So it'll be 3 times negative 1 minus, and then BC, which is negative 4 times 1. Okay? That's 1 over AD minus BC. And then, remember what happens here. 3 and negative 1 swap places. Okay? And then, negative 4 and 1, they just turn into their opposites. So instead of negative 4, you'll have positive 4. Instead of positive 1, you'll have negative 1. There we go. Let's simplify this a little bit. So let's see. The inverse is going to be 1 over. Now, this denominator is negative 3. I see two negatives right here, which make a positive 4 times 1. So it'll be negative 3 plus 4. Negative 3 plus 4, which is just 1. 1 over 1, so that's just 1. So it'll be negative 1, 4, negative 1, 3. Okay? So let's move this up a little bit. So the inverse matrix is equal to, all right, here's the inverse matrix. Negative 1, positive 4, negative 1, positive 3. This is what we're going to multiply both sides of our matrix equation by. See our matrix equation up here? We're going to multiply on the left-hand side and on the right-hand side over here by our inverse matrix. All right, you ready to do it? Let's go. Okay, you guys, here's our work now. What you see in red is the original matrix equation, and what you see in blue is the inverse matrix that you and I found, okay? And so what we're doing is multiplying the left-hand side on the left by the inverse matrix. That means over here on the right side of the equation, we have to multiply on the left by the inverse matrix. You notice that I'm stressing that you have to multiply both sides by, of course, the same thing, but on the same side. So in other words, we're multiplying by the inverse matrix on the left, and we're multiplying the inverse matrix on the left, like that. Okay? So, and the reason why I stress that is because of what we said earlier, that matrix multiplication is not commutative. So the order in which you multiply matters. So that's why I'm making that distinction. Okay, we talked about how you multiply a matrix, right? So this is what you can be sure of. Whenever you multiply a matrix by its inverse, what you do is you get 1. 1, which is the multiplicative identity. So all of this right here, let me see if I can show you. All of this right there just becomes 1. Okay, so I won't even write it. So on the left-hand side of my equation, all I have now is the variable matrix, which is what I wanted isolated. Okay? And on the right, all I have to do is multiply this 2 by 2 by this 2 by 1. All right? So let's do that now. And we worked on this earlier. Okay? It'll be the first row times the first column, right? So it'll be like so. It'll be -1 times 2 plus 4 times 1, which is what I wrote here, right? That's matrix multiplication. The second row will be -1 times 2 plus 3 times 1, which is what I've written here. So what we get is, let's see, we get -2 plus 4, that's 2. And then down here we get -2 plus 3, that is 1. So there we have it, you guys. Our final answer, the solution for the system is 2, 1. This system of equations represents two lines that intersect at the point 2, 1. And we found that by multiplying by an inverse matrix. Okay, everybody, next example. Use an inverse matrix to solve this system. All right, cool. Let's go again. Another example. Let's set up the matrix equation. So we first have our coefficient matrix, and then we'll have our variable matrix, and then on the right we'll have our constant matrix. Okay? All right, so our coefficient matrix is 5, 4, 3, 2. Our variables are x and y. Our constants are 11 and 7. So there's our matrix equation. What we want to do is multiply both sides by the inverse of the coefficient matrix. All right, so what we need to do right now is find the inverse of the coefficient matrix. So let's do that right now. Okay, do you remember what we need to do? I would love it if you could pause the video and find the inverse of this matrix. Okay, so I hope you paused it, and I hope you're back now and gave it a shot, okay? What I'm going to do to find the inverse of this matrix here is swap the 5 and the 2, and then I'll do the opposite of 4 and 3, okay? So, and I know I'm not done right there, but actually, let me move that over. Okay, so 5 and 2, swap places. And now I have -4 right there and -3. And then in front of this, I have 1 over AD minus BC. So it'll be 5 times 2 minus 4 times 3. Okay? All right, did you get all of that? So let's see. This turns out to be 1 over right here, you have 10 minus 12, that's -2. Okay, so they got -1/2. And then you have times these entries here, which are 2, -4, and -3, +5. Let me move this up a little bit here. So you can see that your inverse matrix now, remember this is scalar multiplication, distribute this -1/2 into this entire matrix. Okay, so what you're going to have for the inverse is All right, you're going to see negative 1/2 times 2 is negative 1. Negative 1/2 times negative 1/2 of negative 4 is just positive 2. And then negative 1/2 of negative 3 is just positive 3/2. And then finally, negative 1/2 of 5 is just negative 5/2. So this is the inverse matrix, and this is what we're going to multiply both sides of our matrix equation by. Okay, you guys, I have it all set up now for us. So what you see in red brackets is the original matrix equation, and what you see being multiplied on the left side on both sides of this equation is the inverse of the coefficient matrix that you and I found a second ago. All right, now I told you that whenever you multiply a matrix by its inverse like this, that you just get 1. So all I have left on the left-hand side now is my matrix equation, xy. My variable matrix is what I meant to say. My variable matrix. All right. Now on the right-hand side, I am going to have to multiply these two matrices. Now we practiced this already. It'll be negative 1 times 11 plus 2 times 7. All right, it's negative 1 times 11 plus 2 times 7. That's all that. We've got to figure out what that'll be. And then 3/2 times 11 plus negative 5/2 times 7. That's what I wrote here. So we have a little bit of fraction work to do, but you and I will make it out alive. Okay? All right, so let's see what we're getting here. So x and y are. So let's see. This is negative 11 plus 14. Negative 11 plus 14. Let me actually write that out. Okay. Now on the bottom row, or in the bottom row, I have 3/2 times 11. Don't forget that the 11 has an invisible 1 underneath. So then when you multiply, you're just going to get 33/2, right? And then minus, over here, you'll get 35/2, like that. Okay? Just about done here. So that means you're going to have your variable matrix, x, y, right? Like that. Okay? And then over here, you have your solution. So you'll have 3 up here. And 33/2 minus 35/2 is negative 2/2, which is just negative 1. Okay? All right. So the point of intersection, the point at which these two lines are meeting or intersecting, is 3, negative 1. All right, everybody, this was a long lesson, and I'm going to cut it off here, okay? So there are a couple things that I did not go over, and I think this will be a good place to stop, and we'll call it this section finished at this point, okay? So 6.4 is done. Matrix operations and solving systems using an inverse matrix. Good work, good job, and I'll catch you later.